all the people sitting here. Understanding my talk is the barrier between you and the lunch, so I try to do my best to make it worthwhile for this video. So I'm going to talk about a binary translator that translates 32 ARM binaries to run a 64-bit processor.
64 ARM.
A 64 ARM processor. Yes, there we go. So here's a little quick overview of ARM history. You know, at the beginning we have 32.
26.
20. There we go. I agree. And, approximation. So 2012, I guess we had the first two 64 bits, and today we see many ARM V8 processors supporting both 32 and 64. And is there a tomorrow that we're going to see 64-bit only? So I only know those two. Anybody know more?
I would guess the Apple chip, although they don't say.
Apple chip?
The Apple
A11?
A11? Because
A11 is not.
It's not? Okay.
If I check. So on the next page, I'm going to talk about that. Anyone else? I'd love to know, but
I know the answer, but I'm not going to say.
Okay, that's a good answer. So, so Apple is pretty aggressive moving to this direction. You know, 2013 they had introduced the 64-bit shortly after basically the 53 and 57. 2006 last year they started to put the warning signs in the in the app. Basically says you know 32-bit support will be stopped pretty soon. So and it happened. It happened actually last week. The official iOS 11 support is the first iOS that does not support 32-bit. So the guess is, so A11, the ones currently powering iPhone 10 and iPhone 8, as far as I know, has 32-bit. So since the iOS from now on is going to be 64 only, in theory, from next to the chip, or they might start to drop it. So that's my guess, but nobody knows. But in companion movement, all the Mac Store must support 64-bit, and Mac OS next year will become 64-bit only as well. So clearly, there is someone is moving pretty aggressively on one side of the world, and the other side of the world isn't very pretty. So we did, end of last year, we did a little survey, just pick top 100 Android apps. What we find out is...
That's got better. That's better than it was a year ago.
Okay, in terms of what?
In terms of either pure Java or 3264 support.
More pure Java?
Yeah, there's much more pure Java.
Oh, okay.
It used to be about 4%.
Wow.
So,
okay, that's even
an
more.
improvement.
Okay. So I just came to this. Anyway, we did a survey. So there are about 16 pure Java, and there are only 2% with both 64-bit and 32-bit, and vast majority, 82% are 32-bit associated libraries, which means you know you need a 32-bit CPU support. That really is a huge sort of. I mean, really, 82% is quite a bit. So, that clear seems to be some gap there, and for a few brave souls, start wondering, including myself. So, does binary translation actually would at least bridging the gap? We all know the true solution should be the hardware support and a pure, beautiful 64-bit world. But given the situation, is that possible? We have a path to move there a little bit more smoothly, and you can't really tell the picture. I kind of grabbed from the internet. What's really saying is the binary here 666, the evil second numbers from. Anyway, this doesn't matter. So here's a little bit sort of rundown of basically Google search, Wikipedia, and our own knowledge, a couple of notable binary translators. So the effort has been done before, not massively, but some of them are pretty successful, mostly in the dynamic translator area. So this one I found from Wikipedia. So is that true? Anybody know this about it? Okay. Anyway, so there's not many static binary work as far when I did my research, or successful ones. But there are quite a few well-known dynamic translators are well-known. Obviously, if you really stretch the definition of that, using architecture level, QEMU is the most well-known one. But at the system level, what I call user level, you see quite a few. Apple did it twice when they changed their architectures, and the DEC did one. There should be one I forgot to put. I think Intel, when they moved to Italian, they also had one. Yeah, I should list that one. And my understanding is some of that work became the foundation of the Houdini, which is also used in the Android ecosystem. So this has been done. So that's kind of encouraging for us, but also scary. So anyway, I'm just going to get into my main topic. That's a little bit intro. So we call our translator Salsa, mainly because their predecessor is called a Mumble. So, and it was based on a PhD work by Amnil, and he's from University of Manchester. So we did quite a bit of extension based on that. We combined both static and the dynamic translating techniques in our total solution. I will get to that later. And it translates full 32-bit ARM instructions and targeting Linux and Android, not surprisingly. So here's a very grossly simplified architecture view of the dynamic translation part. As you can see at the bottom, you have a 64-bit kernel, and you need the 32-bit syscall to be present. It should be obvious now or later. And on top, when you translate the 32-bit code, which is 32-bit binary here, you really wrap it around with the 64-bit translator process. That's why it started to have a relatively pure 64-bit process to the kernel point of view. However, there's quite a few tricks that's been happening while you're running that. First of all, you cannot really run it. So there's the so-called ISI translator actually does the translation from the 32-bit code to a 64-bit code. And then it starts to run. Because it's a 64-bit code, you can run on the CPU. However, while it's running, you will frequently use what we call system interacts with the system, the environment, like syscalls, those kernel interfaces like proc interfaces. So when you do that, logically speaking, they go through what we call system emulator, which is trying to create an illusion that this process is still a 32-bit process, while in reality it's 64 process. And going through that, obviously you get to access to your original familiar 32-bit syscalls so that this program is still happy. And obviously, occasionally also may cause to 64-bit for a few cases. So that's just the overall, like I said, a grossly simplified architecture. This gives a little bit of more implementation view of how the translator actually work. Thanks to 64-bit space, so we actually have luxury to reserve, which by the way Houdini doesn't. We actually have the luxury to reserve the whole lower 4 GB space entirely to the original 32 bits. So from memory view perspective, you will see almost identical, pretty much identical to as if 32-bit program was running. Your code will be loaded into the original place, and you will have the heap when the original code calling malloc, actually a part of heap will be allocated in the lower 4 GB, and the original stack will be largely preserved as if they were running in 32-bit mode.
But isn't it not a problem that you have 1 GB more than it should have? Because the only has 3 GB, not 4.
Good question. So I actually forgot the detail whether we still put it in the 3 or 4. But anyway, it works. So good question. I actually forgot about this detail. So then the translator actually will take obviously the upper part, and then we'll translate the code, translate the heap, and this new section basically holds the translated code. So roughly speaking. And here's touches a little bit of basic how translation actually works. The basic element for translation is called fragments. A fragment, so I give a very simple code here, a function where it's very stupid things. If greater than x, you return z, set z to 0. If not, just do a subtraction, return 0. So this is what we translate into. And if you look at this code, we actually have 4 different fragments. A fragment is a single entry continuous block of code. So the keyword is single entry. The second keyword is contiguous. So you see the first fragment is starting from the function until there's a branch. Because if you extend beyond that, you would have 2 possible entries, right? Okay, that's good. And so by doing this, we find 1 fragment, we find another one, and then we find the 3 actually goes all the way to the bottom. But we also find another one, which is 4, because this one will jump here when this condition satisfies. You will go here, basically. So you get the idea. Code basically just, when you go through this code dynamically, you identify fragments, and then you translate it based on the, so I'm jumping ahead. So then you kind of translate it based on the fragment basis. You just do 1 fragment by another fragment. So this is given on the first fragment, where the left is 32-bit instructions and the right is actually the 4-bit instructions, how the fragment is translated into. And you will notice that while this corresponds to the original code BLE, there's a one here. It was meant to connect a next fragment, because if you have a branch, possibly what's following up, there's 2 possible fragments, right? One is when branch is true, you go to the targeted area, but then if not, the next one. So next one we don't really translate, so we insert another branch, goes back to basically translate itself, and the translator will find out whether the next one is already translated. In that case, it will just, I think I'm not getting ahead of myself, and it will just let the control flow go there. Yeah, so I'm a little bit getting on myself. So basically, a fragment will return to the dispatcher, which is part of the translator, when it's uncertain about the next instruction or next fragment it is. And dispatcher will find the next fragment executed if one already exists, and otherwise it will ask the translator just to translate 1 block and generate another fragment. And in either case, when the first branch happens, it will do what we call direct linking, just basically at the runtime modify that translated cache to directly jump to the target fragment in the future. So in the future, it doesn't really come back and forth. So that way you really have faster runtime efficiency. So that just gives an idea how actually translation works and how the translated code execute among themselves. Here a little bit more details of the translation. Here shows how 32-bit registers mapped into 64 bits. On the integer side, very thankfully, we have many more registers, so we can do one-to-one mapping, and then still got quite a few at the disposal for us to use for various purposes. But for floating points, we are out of luck. Basically, this one shows in 32-bit space, you could have many different ways to address floating point registers or neon registers. The most notably is you could have 32-bit single precision register address them, and then you could still address the double position from 16 to onward to 30, 31. That will give you basically 48 different addressing at the same time, possibly, even in the same fragment, basically. So that will be the challenge, because on 64-bit, even though you have 32-bit, 32 registers, they really don't have that many to allow us to do one-to-one assignment. So that's one of the challenge. So to do that, so there's two challenges. Like I said earlier, the floating point could use up to 48 different floating point registers at the same time in the same fragment. And also there has various different aliasing effect from 64-bit. For example, here, I don't know if anybody write code explore aliasing effects. Maybe other people can help me. But still, architecturally, we have to make sure it's correct. I mean, we cannot assume code doesn't do that. So basically, I mean, like I said, if you modify this register and later on you kind of accessing D0, you will find the value is changed, and you will see S1 doesn't really corresponds to D0 here. It doesn't change exactly the same way. So basically, we cannot say D0 equals to D0. We're done. We cannot. So that's a little bit unfortunate. So that's also the challenge we're having to.
The only time when people use that kind of packing
Yeah.
is with the vector registers. Is if you look at it as a vector register, then only do they use that kind of packing, because some people might be interested in the individual lane elements. But if you are looking at it as single precision values and double precision values,
Right.
it doesn't make any sense.
Right.
Because the format is decided in the register.
Right. But for SIMD, don't people, I mean, sorry, a little bit sidetracking. For SIMD case, don't people just always stick with this kind of usage because there are enough instruction and ways?
No, but that is when you have
they will still go back to that?
No, they won't go back to that. But even in the SIMD registers, whether it's AR32 or AR64, they can access the individual elements of the vector.
Right. Right.
So you have 4 single precision elements, or 4 32-bit elements inside a 128-bit vector.
Right. I understand that. So in the SIMD case, and actually we do have perfect mapping. So if people write good code, we actually don't really have that aliasing effect that I was really referring to. But anyway, we do have this. To be architecturally correct, we do have to worry about that. So what's the solution? The solution is allocate. So basically, we actually allocate memory blocks to store the floating points and registers value. So that's the official backing where value is. However, the performance would be suck if you actually do that. But dynamically, we assign 64-bit floating points as kind of caching to that memory backing of the register. And then at any moment, meaning in any fragment, we actually remember what we call register binding, which register is assigned to which 64-bit register. And hopefully, and in most cases, fragments don't really use floating points, but even if they do, they don't really use more than 32, for example. So that get by nicely for the most of the time. However, it does create a problem that it could, what we call, result in multiple translations of same fragments, because fragments may have different incoming path and may already have different sort of register bindings at that moment. So for the speed reason, we might have multiple translations of same in the expense of memory, basically. Solution 2 is basically whenever a write to the FB register happens, there's a invalidation mechanism. Again, it's part of the register binding data structure. It will propagate through the code to tell us whether the particular caching is still valid or not. And if it's not, you generate a code that actually does a load from the memory. Okay, so far we covered some aspects about the translation. We move on to some aspects of the system emulation. The first one is system calls. The original 32-bit generates 32-bit system calls. So majority cases, 32-bit calls will be just what we call redirected to the original 32-bit calls. We did a little bit of hack here. Because the syscall number, they overlap 32 and 64-bit, so apparently we cannot issue the same one. So we kind of played a little bit hack and added one more bit to the syscall numbers, and then kernel needs to be modified, recognize this is a special call to 32-bit, and quickly route it to 32-bit side. And then there's a couple of others for special cases like signal handlings, exec. Those, because they have slightly different implementation or meanings in the translated environment, so we have to do it ourselves. And some purely just for performance reasons, we also intercept implement with 64-bit or libc. The next aspect is related to runtime is loading elf. So because now you're running Translator, nobody is doing this job that kernel would be doing when you're loading a 32-bit, meaning setting up the stacks and do the man map of the original code. So basically, Translator would do that on startup. Basically, will do the same job that kernel would do. So most of it, including man map and executables in the lower 4 GB space of the code being translated, and set up the stack, and also additional step loading the interpreter if that L file requires the interpreter to do it. Threaded and forking. It's kind of messy, but the key idea is one objective was to share the translated code among different processes, different threads, sorry, not processes, different threads. So by doing that, necessarily you introduce some coordination between thread, which is not visible to the original program. So by the way, Translator does not have its own threading. It always sort of hijacking the original program's thread. And then when you actually translate, any thread could start translating. Depends which is the first one to hit that code that doesn't get it translated. So it's in the same memory address space. So one of the design goal is we got to keep this shared, otherwise the memory usage will kind of blow out of the roof. So in order for that to happen, like I said, there are thread coordinations that must happen. That doesn't exist in the original code. And because of that, the forking and the threading needs to be very delicately handled by the translator. Signal is another messy areas. I probably don't want to get into too much detail, but the gist of it is obviously the translator intercepts all the signals, and then it will try to find the right time deliver to the original code. By that I mean jumping into the signal handler from the original code after translating them. And the tricky part usually involves, for two different kind of signals, they have different kind of problem. For synchronous ones, they're mostly caused by the instructions, like seg faults of the load instruction and store instructions. So for that, there's actually a table was stored aside by the translator for every such instruction generated. And whenever, when you're actually running the translated code, when that happens, the control goes back to the translator, and translator will look up at the table, and we'll find that instruction. At that moment, we reconstruct the 32-bit signal contacts, and then jump back into the 32-bit signal handler. So that's how that one is handled. Asynchronous is the ones that program is not aware of. You just press Control-C. This one, the challenge is the code might be running in a fragment. And remember, we have direct linking, meaning the code can run in the translated code forever in some sense, right? In that sense, then you don't have a chance to force it to run, to run the signal handler. So that's not very good. So the way we're doing that is when that happens, we actually do a fragment unlinking, and basically find out which fragment the thread is running at this moment, and basically change the sort of last branch instruction and allows them to jump back to the translator. When they come back to translator, he knows, oh, why I come here, because there's a signal waiting for me, and I'm going to do that. So that's the way to deal with asynchronous signals. Guest memory management. So actually, the implementer is here again. Did most of the work. So basically, you have to maintain the same memory view for the original code, because if you don't do anything, the program will, basically, if many programs read a mem map, right, to figure out where they are, what the stuff. If you don't do anything, mem map for 64-bit translator will have 64-bit address space, shows all those funny stuff, and actually a lot of apps just crash basically. So we find out it's really tricky. At the beginning, we're doing this in the translator itself, in the user land, but it's really, really tricky, and mostly related to GPU, some very advanced hardwares. They have extra sort of interaction with kernel in terms of their own memory address. So it's very difficult to get it right purely from user land. So eventually, we move down to the kernel for this particular part. And here's what it does. So we do have a concept that's so-called a translator process. It's a 64-bit process, but the moment they start to issue those compact syscalls, they became what we call translator process when they come from translator. And for them, we have a separate mechanism to track the memory map issued from the original 32-bit calls, and which they should live under the 4GB, obviously. And fail BRK to force C library to mem map, because BRK is really hard to do even with kernel. And then chop off the greater than 4GB so that the notice we use self, so we're only fooling the program itself. We're actually not fooling another process from the system. So if another process from the system try to look at this process map, you still get the whole picture view.
So are you using personality for that, or how do you decide in the kernel?
It's not really personality. Like I said, right now we don't change personality. We only mark this process the first compact guest call happens. We know it's from a process. So in that sense, it's equivalent to personality, but not using personality. Yeah. So so I use this place to also mention some other kernel changes. I said earlier, raw 32-bit syscall. The other one is we have to pretend to many driver systems this is a 32-bit process, because if you don't lie that way, driver will not behave correctly. because to kernel you're still 64-bit if you don't lie. So far that's all about dynamic translator, and things works nice. But we found that one big problem, especially on Android system, is the startup time. The reason start time sucks because, as you can imagine, with the architecture I just presented, on starting up, you just got a bunch of code to translate. You got a lot of code to translate, and that takes time. So in our first implementation in Angry Bird, it takes 45 seconds to start up and make the first musical note. I still remember when the first time I was presenting internally I basically says, look, I'm going to start Angry Bird now and then talk about other things. Then when the music comes, I say, listen, it runs. So this is how bad it was if you just did dynamic translation. So the solution we do is to pre-translate. Again, not getting into a lot of details, but the underlying principle is pretty much similar. You're presented the L file statically, not at the runtime. So you kind of first thing you do, you try to find the entry points. So this is the exact classic static translation technology. Find the entry points into the L files. So if you have symbol, you have a better job. If you don't symbol, you try to guess. There's many ways to guess. And then you just follow the control flow, treat it as if you have runtime running through that and generate fragments. There's some nuances in the detailed translation, a little bit different because there are too many passes. You have to cut the trimming, pruning, stuff like that. But the general principle is as if you are running through that code in a static manner, and then you generate a bunch of files. And those files later on will be used by Dynamic Translator. So that basically Dynamic Translator will try to find that file. If found it, then cool. I don't have to do runtime translation anymore. Just use that. So that will save the time. So the end result is, at least on Android systems, we found more than 95% of code are pre-translated. You only dynamically translate this 5% now, which is great. You save a lot of runtime effort in the dynamic translation. And today, the Angry Bird is starting about 50 seconds, which is almost identical to native, actually. I'll get to performance a little bit, but it's pretty amazing. So the main benefit is, a bonus benefit. By doing that, we also reduce a little bit of RAM, because with pre-translation, you can manage memory a little bit better. So as I said, we do support Android. Sparkline is the Android house. So we do get the system running on Android. So I talk a little bit about how we integrate this fundamental technology with Android. So without a translator, you basically can get rid of this I would say orange part. You will have 64-bit art running 64-bit code or pure Java code, and you have 32-bit art running 32-bit code. But since we cannot run 32-bit anymore on this system, so we just wrap around basically the Zygote with a translator. And then if you know Android, how it works, all the applications are forked from the Zygote. So if you start to translate the secondary Zygote, 32-bit Zygote with a translator, and every other just kind of a fork of that 32-bit Zygote, and then 32-bit apps will just run pretty much. So the key things I want to emphasize is it's a whole process translation. So this is different from some other translator technology where they might just translate the 32-bit code itself, a library itself. So here's how pre-translation integrates. This is a diagram shows how when you build an AOSP, you generate a lot of code in the end you build from left to the right. And then we just add some extra step at the very end. feed all the 32-bit part to the pre-translator on the build machine to generate some, what we call salsa pre-translated file and pack into the system partition, basically. So it became pre-translated. So system partition became pre-translated. Application can also be pre-translated. There are 3 areas we looked into how to pre-translate. One is those 32-bit libraries under the libarm. We can look for those SOs and do the translation. And then we can also look at the shared libraries inside APK. The OAT itself is 32-bit ELF, so we could also pre-translate those. The way we actually do the timing to translate it, we peg along DEX to OAT process. Basically, whenever Android end, starting from Android end, they have this background DEX to OAT process where it come up periodically. Usually in the night, it will translate some Java code into native code. So we peg along that process. Whenever that process runs, we also get excited and try to look for opportunities to pre-translate 32-bit into 64 bits. Testing. Yeah, from very day one, we find out this is going to be a fun project because it's just very, very, very damn hard to debug. You don't have, there's multiple layers, and you don't really have source code. For example, you see a bug of the app. The pixel is not right. So I still remember in early days, we have one small hello world bug. And what it does is you push one button, increase the font. You push another button, it decreases the font size. It's just that simple. But from very early days, if you click it many, many times, the font will be corrupted. That's a bug. But really, really, there's no trackable way to debug this. In the end, we didn't really, we couldn't really debug it. It was fixed as a byproduct of some other things I'm going to mention. So that just tells how hard it is. I mean, even though there's a clear bug there, you really just cannot trace through using traditional debugging technology and find out where exactly you did wrong. Just because the symptom is too far away and too many layers from where the source for the bug is injected. So we understand that, or gradually understand more, did many, many different testing. It's almost make me feel like doing a CPU design in software. So we adopted many CPU design technology, basically verifications. We did the translation verification, which is really helpful. And by the way, I get this information here in Linaro last year, so whoever tipped me, I'm really thankful for that. It's a lifesaver. I mean, with the Ritsu, we extended and then really find many, many translation bugs along the way. And then we test the LTPs, while grind, and we did all this Android tests. So far, it's really in a pretty good shape after all this testing. So there's some stuff we could brag about. LTV test pretty much passed 90%. The rest we just cannot pass. It's no limits, basically. There are some of them are related to the clone schedule, and some of them related to the memory. Ritsu has been running continuously with several boards through the whole development cycle. As we speak, it's still testing, but gradually you will know they will not find new bugs anymore. In the last couple of months, they stopped to find new bugs, but they're still running. By the way, Ritsu, I probably didn't say it very clearly. It was a random instruction generator, generated 32-bit code, and then threw up the translator, and then you can run it in the translator, and you can also run it in a native hardware, 32-bit hardware, and then you compare the contents to see whether there's anything wrong or not. So that's what Ritsu is. And we actually did quite a bit of extension to Ritsu Plus, where original Ritsu is a pure random, meaning generate instruction by one instruction. We're actually able to generate a sequence of instructions. The reason you generate a sequence, you generate more realistic dependencies and much more productive to reveal new bugs. also matches the fragment sort of structure a little bit better. So yeah, so we're still. I think actually we fixed the last bug, or it disappeared. So I actually was calling my guy yesterday night, and he said with the latest version of that app, it doesn't appear anymore. So we don't know really what happened. It could be actually an app bug. It's just when you move to Translator, it shows up because the bug itself actually is a high-level error. So there's some performance here numbers. We tested on Nexus 5X. So what we did is you strip away the 64-bit shader library, and then just run the APK. And you can turn on Translator or turn off the Translator. So we started with Geekbench 3, so we were pretty happy. See, degradation is relatively small, but then when we moved to Geekbench 4, it seems to be much larger, but we will take it. There's also, we also did the CPU spec. I'm not going to get into detail, but I guess one number might be interesting to the audience is 16. Average degradation is around 16%. So you kind of will get an idea what is the runtime efficiency loss. So there's a couple of others benchmark which is not. I would say it's not as good as those, so I didn't include anything strategically, not including in the slides.
So why did you give the performance number for the high key rather than the spectrum processor?
Because actually, I'm not authorized to disclose anything we're doing. So far I didn't even say we have a processor, right? Did I? So this is research, academic research.
So, what about the two lines that got better with the translation?
Yes, we actually see quite a few times the translation better than the original code. Not just one case. In some other tests we also see. Honestly, we don't really know. I mean, but we can guess because a lot of times the performance is affected by the cache behavior. So when you translate it, you might be perturbing some of the cache characteristic. So that's our best guess. Yeah.
So one question on benchmark. So what were like the worst cases? Like was it like 20 times slower, 100 times slower, or?
For general apps, it's a blended case, right? There's no apps really So for the blended, my mental sort of degradation typically I give like 20%, actually, even a little bit worse than 16%. So generally I would say 15 to 20 seems to be right for general blended workload. But if you want a worst case, actually we do find a worst case. We didn't investigate, but if we investigate, we might be able to sort of work around it. We do have a really bad case here, actually, just to prove we didn't lie. So there's one actually double. So you rarely see any workload at double, but this is actually one of the extreme case. What is it? SJENG, whatever. SJENG. So that's actually pretty bad.
But what if you try to run something like JIT or like Node.js?
Yes, very very good question. I did not include it here. JIT was one of the performance we worried about from day one because browser generated JIT and also many applications are browser pages. So we use SunSpider, which is quick to run. We probably could have run some others. What we find out is on different browsers they have different degradations. We do have browser-specific optimization as well. Actually, inside the translator there are JIT-specific optimizations. Those are heuristics. We kind of guess how JIT would work, and we do some tricks to make it faster. So SunSpider on Chrome OS is 2.3 or 4. 2x, basically 2.4x slower than native. It's actually pretty good. Consider when we started it was like 20, 30, but it will quickly get down to 15, and then 15x worse in terms of that. And then we kind of going slower to get 2.6. And Houdini is 7x on JIT. So that's actually a pretty good achievement. And like I said, there's a couple of things I don't feel too proud in the put here. They're mostly related to memory usage, RAM usage. RAM usage, it depends on how hard you squeeze. It was the overhead is roughly about 60% to 100%. Basically, you think about a double the RAM usage. And then there's what's the other one? You do use more storage because you pre-translate, right? Pre-translation is also I think it's roughly equivalent to the original ISO size, so you can sort of think of double as well. So there's a couple of other things. So anyway, summary, it's a scary journey for us too. There's many roller coasters, there are many things we feel like we couldn't fix this damn bug and this thing is never gonna work. But in the end, we did it pretty good. And it's proved it's possible to do that. Well, tomorrow, I guess, people is here, 64-bit. We're ready for that. Hopefully that day comes sooner. So that's it.
So what is the tool you use for the static translation?
Tool?
Yes.
You write by yourself.
Right.
Okay.
Basically, the discovery is you write by yourself, and then translation we reuse basically the dynamic translation, like I said. Yes.
What's your translation efficiency? How many 64-bit instructions per 32-bit?
Yeah. So like in terms of the size, basically like one instruction, how many it goes into. We had conflicting numbers. By the way, we have a very small team. I mean, the total, Ken is already here. You already see more than 20%. So I think a core team is only 5 people. So that's why we don't have answers to all the interesting questions, I would say. If I had the Intel resources, I would have answers to all those questions. But I think the instruction, what I call blutation, it was a little bit fuzzy. The picture there is pretty fuzzy. Because at one time we had a so-called like 20% sort of blutation, but I don't feel that was right. So when that was measured, basically that looked at one fragment to another fragment in translation, like strict translation. And when you blended the workload, of course it also depends on the workload. But we ended up also have what I call miscellaneous auxiliary code generated, not necessary to the translation. We generate new code, for example, to jump in and out the dispatcher. And then we also have like code cache organizations, and when you do amount. So if you're adding those together, I think the percentage could get much higher. If you force me to guess, could easily reach 50% more, something like that. Yes.
So a couple of questions. First of them is about Zygote. So the 32-bit applications start from the Zygote, which is doing the emulation. So therefore, you're not getting the benefits of just emulating the GNI level. Is that correct? So in your system, you still have 2 Zygotes running all the time. One is for the 64-bit applications, and one is for the 32-bit applications that everybody.
Correct.
Then the second question is, most of the Android applications are Java-based, but some of them, as you showed in one of your first graphs, have a big chunk of native code. I think in theory for Java code, there are benefits from running on a 64-bit architecture, because you can do Java long, C1 operations, you can do Java doubles, and so on. So right now in the system that you described, you have 2 translation layers for Java code.
Yes.
So have you considered going down the route where your ARC virtual machine is generating IP32 AR64 code directly?
Right. So we thought about that. We thought about as a tactical solution, we could directly modify art to generate 64-bit directly. So again, without getting into detail, not only it takes a lot of time to do, but also conceptually is not. It's actually hard. Architecture is hard. The reason it's hard is because you are actually doing a virtualization, and you have to present this sort of ARH32 nicely. By doing that, you're poking a hole, and a relatively big hole between this nice isolation between these two worlds. And we thought about it possibly when we do JIT. We thought about poking holes. We did some experiment, but eventually it's not here. We actually did something what we call poking a hole in the isolation emulation. But if we want to do what you said, it's poking not just a teeny hole, it's poking a much bigger hole. And we don't have a nice architectural model how to accommodate that. So, but we did think about ILP32. And if you have, imagine if you have ILP32 art, then you might be able to do something hybrid in that domain. Don't know, but possible. Yes?
When you were talking about your signal handling, you mentioned you treat synchronous and asynchronous signals differently. So what happens when an asynchronous signal happens and you jump back to your code to exit and then you hit a synchronous signal?
Let me repeat. What happens if asynchronous happens? I jump to.
You said when an asynchronous signal happens, you unlatch the end and return to your translated code.
Yeah.
But if you hit a synchronous exception before you exit that block, what happens?
Oh, if that happens, actually, I actually don't know because the implementation. But if I ask me to guess, I think the second one will be blocked. But then it will be a problem, I guess. Very good question. Maybe the last bug is caused by this. I'll find out. I don't know. I think yeah. I tend to say I think we do block. I'm not sure if in this case we actually, because treated as a different class, we will let it go and then treat it differently. But very good question. Thank you.
Did you run into that bug before?
I've done the signals before.
Okay. Any other question? No, I think it. Let's stop. I guess. Thank you.